last video, we talked about molar mass, the mass of a mole of particles. That you can use the periodic table's masses in grams, which is how we would want to use them in the lab. We just have to be aware that, for example, if I measure the mass of carbon to be 12 grams, in grams those masses represent 1 mole of particles. So we call it the molar mass. We can calculate the molar mass of a compound similar to the way that we determined the molar mass of these elements. The only difference is that with a compound, I have multiple atoms all chemically bonded together. So I'm going to need the formula. First order of business, carbon dioxide, CO2. Now I just use my periodic table. I'm going to find the molar mass of the individual atoms. We're going to add them up to get the molar mass of the entire compound. With my molar masses, I usually try to go 2 decimal spots if possible. If you want, you can go more, but I try to at least leave enough precision to get 2 decimal spots. So carbon has a molar mass of 12.01 grams per mole. And in this compound, there will be 1 mole of carbon atoms. Then I've got oxygen. I look up its molar mass on my periodic table, 16.00 grams per mole times 2. Then you guessed it, you just add them together. You plug this in your calculator, you add them up. And I would have a molar mass of 44.01, and again, I like to say grams per mole. Just so that I don't get it confused with like the mass of a particular atom or molecule, which would be crazy. 1 molecule of carbon dioxide doesn't have a mass of 44 grams. That's a mole of carbon dioxide molecules. That would have a mass of 44 grams, 6.02 times 10 to the 23rd molecules. If I have an ionic compound, I need to find the charges. So I know this is ionic. I have a metal. This is manganese plus 4. And hydroxide, a polyatomic. So I look up its charge and its formula, which I will always give you, the polyatomics, their formulas and charges, but you have to recognize when to look them up. So some of these common polyatomics you might just get real familiar with. I'm going to need to make this neutral so that the electron transfer is the same, meaning I need 4 hydroxide. My formula then, Mn for manganese. Hydroxide is OH, but I'm going to need 4 groups of hydroxide, so I need the parentheses. Then we just start adding everything together. I have 1 manganese, 54.94 grams per mole. And in this compound, there will be 1 mole. This time, oxygen and hydrogen. Do you remember how you have to distribute this 4? If I have 4 groups of hydroxide, I really do have 4 atoms of oxygen and 4 atoms of hydrogen. So I need to take that into consideration when finding the mass of the compound. Oxygen was 16.00 grams per mole times 4, and hydrogen 1.01 grams per mole times 4. Then I can just add these all together. Plug them in your calculator. And as long as you got the formula right, adding up these molar masses, this isn't so bad, is it? We'd be looking at 122.98. And now different periodic tables will have different molar masses. So if you are using a different periodic table and yours added up to be something a little bit different, totally fine. A+, totally fine. Now when you do these on a test or a quiz or any kind of an assignment, I honestly don't need to see any work. You don't need to show me like 54.94 times 1, oxygen's mass times 4. I trust that you can do that in your calculator. You just plug it in. But the one thing that I do want to see is your formula. Because can you kind of see that if you get the formula wrong, you're going to have the wrong mass. But what if you wrote the wrong formula and you did do the mass correctly? I can give you partial credit. What if by accident you thought that was Roman numeral 6? So you wrote the formula as manganese 6 hydroxide. So your molar mass is going to be a little higher. You have 6 hydroxides instead of 4. But again, if you calculated that mass correctly, I would give you partial credit. On the flip side, if you wrote the formula correct, but maybe you forgot to distribute the 4. So you forgot that it should be 4 oxygen and 4 hydrogen. But if you have the formula correct, I can give you some partial credit. So this in here, I don't need to see that. I trust that you can add and multiply on your calculator. But show me this. This will explain why the mass might not be correct. And finally, what if we had a mole of lead-3 carbonate? Lead is +3. Carbonate is a polyatomic group, -2. So to make that neutral, we probably need 2 lead and 3 groups of carbonate. +6 -6. Electrons are totally transferred. So my formula would be lead 2. Carbonate is CO3, and I need 3 groups. So I must use parentheses. Now we start adding them up. All right, so there's going to be 2 lead. So in my calculator, this is what I'm going to plug in. Lead is 207.2 grams per mole. And that's actually all that my periodic table lists. Usually I go for 2 decimal spots, but this one only gives me 1. I'm going to multiply that by 2. Carbon. My periodic table says about 12.01 grams per mole. And remember, I need to distribute this 3. If there are 3 groups of carbonate, and each carbonate has 1 carbon, there will be a total of 3 carbon. Oxygen's mass. My periodic table really does say 16.00. There will be 9. I need to multiply the 3 times 3. We plug that all in our calculator. This one's going to be a big boy. 594.43 grams per mole. Per mole. And so again, similar to the individual elements, if I measure these 3 masses, would give me the same number of molecules. And to be more specific, 6.02 times 10 to the 23rd. So if I were doing some kind of a chemical reaction and I needed a 1-to-1 ratio between molecules of carbon dioxide and molecules of manganese 4 hydroxide. If I measure 44 grams of carbon dioxide and about 123 grams of the manganese 4 hydroxide, that would be the same number of particles. That would each have 1 mole of particles. And these chemical reactions are all based on ratios of particles, not necessarily masses. So if I want a 1-to-1 ratio of particles, I don't measure a 1-to-1 ratio of grams, because all of these have very different individual masses. Lead is just a really big atom to start with. So the lead carbonate has a giant molar mass. It's made up of big, heavy atoms, whereas carbon dioxide is made of smaller atoms. So when I'm using these ratios, I need a 1-to-1 ratio of atoms. I want to measure a 1-to-1 ratio of moles. If they have the same number of moles, they'll have the same number of particles. they will not have the same mass. Mass will be dependent on the individual identities of the particles.